In this example, we're giving a disk that has uniform density and a mass m, and we're going to calculate the moment of inertia about the center of mass using polar coordinates. And so the expression for the moment of inertia about the center of mass, and this is planar motion, is we're going to integrate across the body of the position vector of the differential mass with respect to the center of mass, the norm of this squared, and across each of the differential elements. So first draw the differential element, and it's a differential mass that will integrate across the entire body, and this is where dm is equal to rho dv. And when we take a closer look at our differential element, the element itself is located a distance r away from the center of mass, and then if we expand this, then the dimensions here will be dr, and then the arc length, which is related to the distance away, the radial distance away from the center of mass, and this is r d theta. And so then dv, so dm is equal to rho r dr d theta. And this is where theta is defined as the angle, clockwise angle away from the b1 axis or the horizontal axis to define the position. And so if we express this, our position vector, r of the differential element, with respect to g, in the b1 and b2 basis, then it's x in the b1 direction plus y in the b2 direction. And because we're using polar coordinates, x is equal to r cosine theta, and y is equal to r sine theta. Let's place all of these expressions into our formula for the moment of inertia. And so it's a double integral, and then it's our norm of our position vector squared. And so the norm here is r squared cosine squared theta plus r squared sine squared theta, and we're multiplying this times rho dv, and dv is r dr d theta. Our bounds of integration for each of these expressions, so for dr will be from 0 to r, and then for our theta bounds, we're going to come all the way around the circle to create the disk, and so that'll be from 0 to 2 pi. We'll start out by integrating with respect to r, so we'll distribute the extra r that we have into each of these terms. We'll have an r cubed term, and then the expression after integrating with respect to r and applying the fundamental theorem of calculus looks like this. And so now we're left to perform the integral across d theta. And so the terms that we have here are a cosine squared theta and a sine squared theta, and we need the help of a couple of identities. So we'll use the double angle identity, in which we have cosine 2 theta is equal to 2 cosine squared theta minus 1, and also cosine 2 theta is equal to 1 minus 2 sine squared theta. And now with these two identities, cosine 2 theta is equal to this expression and is equal to this expression, we can solve for cosine squared theta, and that's equal to cosine of 2 theta divided by 2 plus 1/2, and then also sine squared theta is equal to negative cosine 2 theta divided by 2 plus 1/2. So we'll substitute these two expressions into the inside of our integral, and after doing so, that we see that we have two terms that are the same but opposite signs, so these two terms cancel, and we're left with a really nice looking expression in which we have r to the 4th over 4, and then integrating with d theta is theta, and evaluated from 0 to 2 pi. And this gives us pi over 2 r rho. We need to take care of our mass, and so the mass is equal to rho times the area, and this is rho times pi r squared, which gives us the expression to substitute. Rho is equal to m divided by pi r squared. And so we substitute this, the mass moment of inertia about the center of gravity. Center of mass is equal to pi over 2 r to the fourth, and substitute in, we get m divided by pi r squared. And then simplifying into m times r squared divided by 2. And so the moment of inertia for a thin disk is, we've just calculated as m r squared over 2. We have the correct units because we have a mass multiplied times a length squared. And then you can apply this to rolling problems or wheel problems now that we have this expression.